In this video, we will explain how to diagnose and test blower motor control circuits, including the blower motor itself and the speed control resistor. As the blower motor ages, the bearings dry out and wear. It starts to drag, causing the motor to draw excess current. The resistor runs hotter and eventually fails. The problem, of course, is that the failed resistor is frequently replaced by itself, when in fact the root cause of the failure is the aging, failing blower motor. Inevitably, the new resistor fails prematurely because the faulty motor was not identified and replaced. This table illustrates the amount of electrical work being done by both the blower motor and the resistor at different speeds in a typical blower circuit. As you can see, the resistor is actually performing most of the electrical work at the slower speeds. This infrared image shows that a working resistor can reach temperatures in excess of 500 degrees Fahrenheit. Many blower motors draw between 15 and 25 amps on high speed. That's about 300 watts of energy. It takes a heavy-duty circuit with quality components to handle this workload. This is why it is a good idea to replace both the blower motor itself and the resistor at the same time if either one has failed. At the very least, the blower motor should always be checked for excessive current draw when replacing a failed resistor. Before replacing either a blower motor or resistor, we will need to check for unacceptable voltage drops on both the power supply and ground circuits to the motor, for excessive blower motor current draw, for evidence of overheating or damage at connectors in the circuit, and you will also need to check if there are other issues that need to be corrected which might impact the performance or longevity of a replacement blower motor or resistor. So with this information in mind, let's look at some blower motor circuits and see how they work and how to diagnose and test them. Using customer interview and inspection worksheets can often help you gather critical additional clues that can speed your diagnostic path. Checking fuses at the outset is usually a lot faster than diagnosing the circuit only to find a blown fuse later. Also, finding a blown fuse early can get you pointed in the right diagnostic direction quickly. For example, a blower motor that may be drawing too much current, causing the fuse to blow. Resistor-type blower motor circuits can be divided into two basic types: power side controlled and ground side controlled. In a power side controlled circuit, the blower resistor and speed control switch are located in the circuit between the voltage source and the blower motor. In a ground side controlled circuit, the resistor and the switch are located between the blower motor and the ground point. In this video, we're going to focus on a power side controlled circuit. Here is a typical power side controlled blower motor circuit found on many GM vehicles. Note that the blower high-speed relay is integral to the resistor assembly. Let's accelerate our understanding of how to diagnose a circuit like this by diagnosing a vehicle with an actual problem. This is a 2006 Chevy Silverado 2500 Duramax with manual air conditioning. The customer complaint is that the blower motor only works on high speed. Looking at the schematic, we can deduce that the power circuits, highlighted in red, and the ground circuit, highlighted in blue, must function, at least to some degree, in order for the blower motor to work on high speed. However, we will still want to check that there are no unacceptable voltage drops on these circuits. Since we are working inside the vehicle, we are going to attach one end of a jumper cable to the battery negative post and bring the other end inside the vehicle. We will attach the ground lead of our digital multimeter to this end. This will be our known good reference ground while testing. With the blower motor running on high speed, back probe the power supply circuit as close as possible to the blower motor. The voltage should be very close to system voltage. Here it is 12.6 volts, which is acceptable. If the blower motor was inoperative, we could check the power supply by substituting an alternative load across the circuit. Here we are using a test beam that draws several amps. We are attaching one lead to our confirmed ground and the other lead to the motor power supply. You can see that the voltage remains close to system voltage with the beam on. If there was no voltage available at the motor, we would need to trace the circuit back through the relay and the switch toward the fuse box to identify the open circuit. With the circuit still loaded, either by running the motor or lighting our test beam, let's check the motor ground circuit. Move the positive lead of the digital multimeter to the ground side of the blow motor. The ground lead of our digital multimeter will remain on the reference ground. If the blow motor is properly grounded, there should be close to 0 volts on the ground side of the motor, no more than a few tenths of a volt. Here we are reading about 0.3 of a volt, which is acceptable. If there was excessive voltage on the motor ground, we would need to check the circuit between the motor and the frame, and possibly between the frame and the negative post of the battery. We can check the individual speed circuits between the blower switch and the resistor by setting the blower switch to each speed in turn and then loading the matching circuit at the resistor harness connector with the test beam. Be sure to use an appropriately sized test terminal to attach the test beam to each circuit at the connector. The test beam should light bright and the voltage on each circuit should remain close to battery voltage. If the voltage was less than expected on any of these circuits, we would suspect a problem further back in the circuit, most likely with the blower switch itself. Additional testing would be necessary to identify the exact source of the voltage drop. Since this motor works at high speed, and each of the speed control circuits is checking out OK, we can confidently say that the problem here is a failed resistor. However, before replacing it, we must check the blower motor current draw. Here we are using an oscilloscope with a current probe attachment to measure blower motor current. The current probe can be clamped around either the power or ground circuit at the blower motor. Maximum current draw should be checked with the blower motor set on high speed. You can also use a digital multimeter with an amp probe attachment to measure current draw. Here you can see that current draw on this motor is about 27 amps. Blower motor current draw varies by application, and an exact specification can be difficult to find. Many motors draw between 15 and 25 amps, but you really need to know the specification for the vehicle you are working on. Experience is your best guide here. If possible, compare the suspected motor current to a similar known good vehicle. From experience, we know that 27 amps is well in excess of what we would normally find for this application. Therefore, if we just replace the resistor by itself, it will almost certainly fail prematurely, resulting in the dreaded comeback. So, with the new blower motor, resistor and resistor pigtail installed, blower motor current is now around 21 amps. About a 22% reduction in current and a significant reduction of stress on the blower resistor. We can be confident that both the blower and resistor will most likely last the life of the vehicle. There are, of course, many different permutations of blower motor circuits, but if you understand the basic principles, you should be able to adapt these methods to test them. Here are some additional checks you should make before replacing either the blower motor or resistor to avoid a potential comeback. Thank you for watching.